Welcome to Brain Vision.
In this problem, we're going to be looking at crossed polarizers. So we have incident light coming in this direction, and these polarizers are oriented at 90-degree angles to each other. So this one will be vertical, this one here will be oriented horizontally. So if you want to think of it, this is like theta equals 0 degrees and theta equals 90 degrees. So if you were to just send the unpolarized light through that, it would have no intensity by the time it got through because they're exactly perpendicular to each other. But what we're going to do is throw an insert in there. The insert's just another polarizer that has a transmission angle of theta equal to 30 degrees. Now, what that's going to do is allow some of the light to change direction as it passes through there, and then it won't be totally perpendicular when it goes to the last polarizer, and we'll actually get some of that beam transmitted through. And so what we're trying to find now is what's going to be that intensity that gets through to the end, where it's picked up by some photocell over here. So they've told us that the unpolarized light, so over here, the unpolarized light has an intensity of 150 watts per square meter. And I'll call that SI for the initial or the incident intensity. After it travels through the first polarizer, we know that unpolarized light going through any polarizer, regardless of that angle theta, it's always going to be equal to 1/2 of that initial intensity, just because for unpolarized light, it's spread out in all directions. Half of those directions will be in line with the polarizer, and the other half will just be perpendicular to it. So exactly half of it gets through. So in our case, 1/2 times 150, and we get just 75 watts per meter squared is actually passing along through the next polarizer. So now we have polarized light with this specific intensity hitting a polarizer that's at an angle 30 degrees relative to it. To figure this out now, because we have two cases of polarized light traveling through a polarizer, getting more polarized light out the other side, in this case, we're going to use what's called Malice's law. So you may recall Malice's law, that's the intensity is equal to the initial intensity times cosine squared of angle theta relative to the polarization. So we're going from theta is equal to 0 to theta equals 30. So we'll plug in 30 degrees to this equation here. S is equal to the intensity that is hitting that polarizer, 75 times cosine of 30 degrees. That's squared. So go ahead and plug that into your calculator, and you're going to get something like 56 watts per square meter. And now that's the new intensity that's going to reach the last polarizer. And we just repeat Malice's law again. So intensity here is 56, the incident intensity on that polarizer, times cosine squared. And now let's be careful with what angle we use here. It's actually not 90 degrees because we need to think about it relative to the current polarization. After it passes through that second polarizer, now it's polarized at 30 degrees. Well, relative to that 90 degrees, that's only a difference of 60 degrees. So the relative change in polarization, 60 degrees, goes into our equation there. And then you just plug that into your calculator. And you'll get that the transmitted intensity, I'll call that ST here, is equal to 14 watts per meter squared.